Hello everyone. So I hope everyone is having an amazing time. So we are going to continue our discussion of AIATS plus phase 2. We are going to take it forward from where we left last week, right? And this test was conducted on 16th of February, right? And if you remember, last time we had discussed regarding atoms, right? And under atoms, if you remember, we had done some questions about transition, right? When electron is jumping from one orbit to another orbit, that we had done. And in the weeks prior to it, we had done about energy of electron, okay, in any orbit. So let's say it is residing in nth orbit. So what is the energy of electron in that orbit, right? So let's do some more questions of that chapter. Coupled with it, we'll also be discussing few more topics from your 11th class, right? So if you see, these are from your 11th class. We're doing some really good numericals on that one as well. All right, so let's begin. And under atoms, as I said, we had also discussed this big table, or what you would like to call it, of hydrogen spectrum, right? Let me come over here. If you see, from n equal to 1, 2, 3, and so on, right? Lehman series, if the transition of electron is happening from a higher orbit to the first orbit, then for Balmer series, higher orbit to second orbit, and so on, right? This we had already done. Now let's see what this first question talks about, right? If you see here, it says an electron revolves around a nucleus of, they have not talked about hydrogen atom, right? They are saying hydrogen-like atom. That means hydrogen-like atom meaning the total number of electrons is going to be still 1, but hydrogen-like implies that the Z is going to be different, right? For atomic hydrogen, we had Z as 1, but for this atom Z can be different, let's say 2, 3, so on. Okay, so Z will be something else. So Z we don't know, isn't it? Because if you see here, they're asking the atomic number Z is, they're asking. Then what have they said? They're talking about kinetic energy of electron, and they said in first excited state, right? Kinetic energy of electron in first excited state, meaning n is equal to how much? N is equal to 2. Right? You see this diagram, this was the original orbit of the electron. This is your first excited state, then this is second excited state, and so on. Okay, and the kinetic energy is given, and Z they are asking, right? So if you, let's revise a little bit, right? So if you remember, we had talked about total energy, right? So what is total energy of electron in nth orbit? Total energy of electron, let me write it down for you guys, in nth orbit. Yeah, good afternoon Rakesh. It would be minus 13.6, right? Z square by n square. If you remember, so far we had only talked about hydrogen atom, so Z was 1. So I had said minus 13.6 by n square electron volt, right? Electron volt, right? But what about kinetic energy? What would that be? Kinetic energy, this also we had discussed. Yeah, good afternoon Aman. That kinetic energy is nothing but the reverse of total energy. That means that the kinetic energy of that electron, which would be nothing but half mv square, right? Where v is the speed of electron in that orbit. So half mv square, that translates to, simply you have to reverse it. So plus, okay, so plus 13.6 Z square by n square electron volt, right? And what about potential energy of that electron? Potential energy would be given by what formula? If you remember, minus G m1 m2 by R, right? We did in gravitation chapter as well, right? So potential energy, whereas here in atom, or if you remember in the charges chapter, or let's say in the second chapter of yours, potential energy, we had talked about potential energy becomes minus k q1 q2 by r, just like in gravitation, right? So potential energy is nothing but twice of your total energy. So just double it. So double meaning it becomes 13.6 into 2. Okay, then Z square by n square electron volt. So this was the general formula, right? Now if you come over there, what are they saying? Kinetic energy in first excited state. So n is equal to 2 here. And what was the formula for kinetic energy? Just not I told you, plus, right? So plus 13.6 z square by n square. Z, do we know z? We don't know z. So I'll simply write it as z square by n is how much? 2 here. So 2 square, and this kinetic energy is written over here. How much? Plus 13.6, right? So it's written plus 13.6 electron volt. Okay, and if you see, I can ask a very similar question also over here. So let's say instead of atomic number, I'm directly asking what will be the total energy of that electron in that orbit. So even without finding atomic number, you can tell me the answer, isn't it? Because the total energy is what? The negative of kinetic energy, isn't it? Total energy would be, just put minus sign over here. This becomes your total energy. All right, so let's see. All you have to do is just solve it, right? So just solve it. So 13.6 and 13.6, they get cancelled. So z square, or if you see, z square will become how much? Z square will become 2 square or 4, or let me just write it 2 square. So z will be how much? 2. Okay, so z will be 2. It was a very simple problem, right? I hope a few concepts got revised in this regard as well. So let's do another question from the same topic, right? See here, see this question. The energy of electron in third orbit of lithium plus 2 ion, right? So third orbit, they have explicitly mentioned that it is third orbit. So they have not said it is second excited state. So third orbit meaning n is equal to 3 here, right? And they have also mentioned the atom over here, because see, if in the previous question, the atomic number was not mentioned, but here atomic number is mentioned. Lithium has how much atomic number? 3. So that energy you have to find out. So which energy they are asking about? Kinetic, potential? Yeah, so I think someone is asking, I need class 1 full syllabus test. Where I can get, please? Yeah, sure. You just have to hang on. All these tests, they are already being conducted, right? And with each of these AIATS plus tests, few concepts are getting revised. So you have to keep practicing. All right. I think they are already being conducted. So don't worry. So see here, total energy we have to find out, right? Total energy, what is the formula? Minus 13.6 z square by n square, right? So z square is how much? 3 square. N is how much? 3. So n square, z square by n square, right? If you see here, they'll get cancelled, right? So they will get cancelled. So what will be the answer? Minus 13.6 electron volt, isn't it? Minus 13.6 electron volt, and this, if you remember, this is the total energy of electron in the first orbit of hydrogen atom. And here, that energy becomes the energy of electron in third orbit of lithium ion, right? And if you want to check, you can also check. Minus 13.6 electron volt will also be the energy of electron in second orbit of, just put z is equal to 2, right? For z is equal to 2, in the second orbit, it will again come out to be minus 13.6. Yeah, good afternoon Himanshi. All right, so let's see a different question, right? One regarding your transition of electrons, right? So if you read the question carefully, minimum wavelength of emitted photon, see the word carefully, okay? Emitted photon due to electronic transition in hydrogen atom, right? So why are photons being emitted? Let me also again repeat that. Why are photons being emitted? Just like we studied, when electron is transitioning from higher orbit to lower orbit, it has to lose energy, right? And that energy is lost in the form of photon. And that energy of photon, right? Energy of photon, that is written as what exactly? Right? Energy of photon, it is nothing but hc by lambda, where lambda is the wavelength of photon. And this energy is equal to the difference between the transition energy, or we can say difference between the energy of electron in those orbits. So let's say from, if you remember, right, from one orbit to another orbit it is jumping, it has to lose some energy, okay? And here in that question they were asking about the minimum wavelength. So remember, for minimum wavelength, what should happen? See here, if lambda has to be minimum, what about this energy? It has to be maximum, right? So the maximum, the photon emitted should have maximum energy. That means that jump has to take place from where to where? Let's again go back to that diagram. please remember this diagram, okay? The jump has to take place from where to where? From the top to the right to the bottom, right? This energy difference is going to be maximum. Whereas see, if you see these differences, let's say it is jumping from infinity to 2. So that energy would be less than this energy, right? So for maximum energy, the jump has to be from, let's say, infinity to 1, okay? Infinity to 1. And something else is also missing over here. What is that quantity? If you remember, what was the formula for your wavelength? For finding the wavelength, you need to remember the Rydberg's constant as well. So let's say in some questions, it will already be given. So let's say I am giving you the Rydberg's constant in this way, okay? So 1 by R is equal to, let's say, 90.9 nanometer. This is given like that. Or if it is not given, you need to remember. Okay, so how will we do it? Remember the formula for 1 by lambda, right? In electron transition, what was it? R multiplied by 1 by n square minus 1 by n square, right? What was this n? This n was n lower, this was n higher. So lower and higher. Here electron transition is happening from where to where? Let's say infinity to 1, right? So lower is 1 only, the first orbit, right? Electron has to jump to first orbit. So lower square, and this obviously is infinity, so 1 by infinity is 0, right? So 1 by infinity is 0. So let me directly write down infinity over here, okay? Or 1 by infinity is 0, so I'm directly writing 0. So what does it become? See, very simple. What does it become? 1 by lambda is equal to R, or lambda is equal to 1 by R. And what is 1 by R given over here? If you see, 1 by R is already mentioned, right? So lambda is equal to 1 by R. If you want, I can just finish it off. Lambda is equal to 1 by R, right? And this lambda, please remember, is your, which one? This lambda would be your minimum wavelength, okay? So let me write over here, this is minimum, lambda minimum, all right? So what would be the answer to this question? Right? Yes, good afternoon, Ronak. Very good afternoon and welcome to our session. I hope you are having a wonderful day. All right, so moving on. I hope everyone has understood, right? We had also done 1 or 2 good problems in our last session last week. So please, if you want to do some more good questions, go back to that video and you can just pause and try and then check your answer. All right. Let's go to gravitation. We had already done some concepts in gravitation, right? Like what is the gravitational force acting on the body, right? And what is the gravitational potential energy? Let's say 2 bodies are placed just like that. So let's see what we are doing over here. And if you remember, this was the Earth. And let's say we had also talked about Kepler's laws, right? Kepler's first law, second law, and third law, right? I had mentioned it and also written it down. All right. So if you, let's say, let me discuss about Kepler's third law, right? So Kepler's third law, we will do some good questions on that one as well today, right? What was Kepler's third law? So let's say this is a circular Earth, right? And let's say you have a satellite over here, and that satellite is revolving around the Earth in a circular orbit, right? So in a circular orbit, all right? Like that, okay? And the orbit is very big, so you can imagine it, how it is going, all right? So let's say we have a satellite over here, right? And the center of the Earth, obviously, let's say this is the center of the Earth, and the Earth has how much mass? Let's say mass of the Earth is capital M, and the radius of Earth is capital R, all right? But the satellite is moving in a circle, and the radius of that circular orbit is smaller. So let me mention this small r as well over here, right? So this is your small r, right? Now what will happen if, let's say, the satellite is in this orbit? Now the same satellite is taken to another orbit. So r is changing, right? So what does that mean? That the Kepler's third law, what would that become? See, first you have to know what is Kepler's third law, right? So Kepler's third law stated that t square is proportional to r cube, where t is the time period of that body, r is the radius in which that body is revolving around said system, okay, or said Earth, let's say in this case. the satellite is revolving around the Earth in radius small r. So how will we use Kepler's third law over here? Very simple, right? So if let's say initially it was r1, finally it is r2. So what will we do? In that case, we can write like this, right? T2 by T1 whole square is equal to, right, is equal to R2 by R1 whole cube, right? R2 by R1 whole cube. All right. Now, students generally make a unique kind of mistake in such problem. Let's see what the question is, and I'll tell you what the mistake students usually do. See over here, what kind of satellite it is mentioned. They have said it is a geostationary satellite. Yeah, good afternoon, Jatin. Geostationary satellite. So what does that mean? That the satellite is fixed. If you see that satellite from, let's say, a point on the Earth, with respect to that point, the satellite, you can say it's fixed. What does that mean? That let's say the Earth takes 24 hours to rotate around itself, right? The time period of rotation of Earth about its own axis. So similarly, the time period of revolution of the satellite around the Earth, it will be 24 hours. Okay, so that's what that fixed meaning. So which means this satellite, we already know the time period, right? It is how much? 24 hours. It is orbiting around the Earth at a height of 5 hours. So here students make the mistake. What they usually do is that small r, they take it as 5 hours. If you see carefully, this is not small r, right? If you see this figure, small r has been measured from the center of the Earth to that satellite, right? But here they have said the height is 5 hours. Height meaning what? How much distance? This much distance. This is the height. Height meaning the distance of satellite from the surface of Earth, right? So this is 5 hours. And what about this distance? This is how much? This is r only, right? Because the radius, just now I said, the radius is r. So what will be small r in that case? Small r will be how much? So small r will be r plus h, which are capital R plus h. Okay, let me write over here. So capital R plus h. So what would that become then? You see, R1 would become capital R plus 5R, and this will become 6R, right? And you already know that the time period in the first case is how much? 24 hours. All right, so let me read the full question as well for you guys. Height of 5 hours above the surface of the Earth, where they have already said R being the radius of the Earth. And the time period of another satellite, they are asking, in hours at a height of 2 hours from the surface of the same planet. You see, they have not changed the planet, they have changed the orbit, right? So in a different orbit, at height of 2 hours, another satellite is roaming, right? So if you see, another satellite at a height of bigger height, or let's say in this case, a smaller height. So if you take it to a bigger height, the obviously time period is going to change. And similarly for smaller height as well. Now for this one, what will be the small r again? The same formula you have to use, right? So R2 will become how much? Capital R plus h. H is how much? 2R. So here R2 is 3R, right? And here what are they asking? Time period they are asking, right? So I see over until now I've just jotted down whatever was written in the question, right? So nothing new we have done. What is new we are going to do right now, which is Kepler's third law. The moment you see the question, Kepler's third law has to flash in your mind, right? So let's use it. T2 by T1 whole square is equal to, that's what we wrote just now, isn't it? Let me write it again. See, T2 by T1 whole square is equal to R2 by R1 whole cube, or instead of T1, let me just directly write down for you guys. What was T1? 24 is equal to R2 by R1, right? R2 was how much? 3, right? Yeah. R2 was 3R, R1 is 6R whole cube, isn't it? So what does this become? See, 1 by 2 whole cube, right? See guys? Can you find the answer? Yeah. Can you find the answer? This becomes 1 by 2 whole cube, and that becomes 1 by 8, right? That becomes 1 by 8. Yeah, so Parnika is asking if they ask at another planet, sir. So if you remember, I had also derived formula for time period, right? Time period obviously depends on R, but it also depends on a few other things, right? Because time period of any satellite can be written as 2 pi r by v, 2 pi r by v, and that v will also be related to mass of that planet. Then mass of that planet will be written as density into volume, right? So what does it become is the time period, it also depends on density of the planet along with R. So let's say for same planet, if you are doing this, changing the orbit, right? So if we take the ratio T2 by T1, etc., the density term will cancel out. But for another planet, if we do, you have to write the full expression. Okay, so this T square proportional to R cube, you won't be able to use. The density term will also come over there. Okay, or if mass is given, then mass term will also come over there. So I hope, Parnika, the doubt was clear to you. All right, very well. So you just have to solve it, right? So what does it become? See here, T2 square, right? So you can take square root both sides, right? So this becomes how much? T2 by 24 equal to, we have taken square root both sides. Square root means 2 is gone, then square root of 1 by 8. 1 by 8, 8 square root is how much? 2 root 2. So we can write this as 2 root 2, right? And bring this 24 over there. 24 by 2 becomes how much? Let me solve it as well. So T2 becomes 24 by 2 root 2, right? 24 and 2 will get cancelled. 6, right? 6 by root 2, right? Solve it. Yeah. So let's, I hope that question and the concept was clear to you guys. All right. Okay, so let's jump to another topic, escape velocity. Right, escape velocity. So what does this signify or imply? Escape velocity, just as the word implies, right? It means that a velocity is given to a body so that it escapes. Escapes from who? Let's say in our case it was the Earth, right? So if you see here, Earth, right? Earth, a satellite is revolving in a particular orbit. Okay. So if we want this satellite to escape, what do we have to do? We have to provide some energy. Okay. So let's say our body, right? A body is at surface of Earth. All right. Surface of Earth. That means what is the separation, or let's say what is the potential energy of that body? What would that be equal to? Right. So what would that be equal to? Potential energy will be how much? We had discussed it, minus G m1 m2 by R, which is the separation, right? So it would be minus G, let's say mass of the Earth is capital M, right? And mass of our body is small m. So minus G mm by small r, right? Or let's say in our case it will be capital R because it's already lying at the surface, right? And what would be the kinetic energy? Remember, we have provided some energy to it. So it gets an escape velocity, right? And let's say the escape velocity is VE. Okay, so what would its kinetic energy be? Half m v square or half m ve square, right? And also remember, escape velocity is the minimum velocity which is required for that body to escape from the gravitational pull of the Earth. So let's say if you are providing a higher velocity, or let's say higher energy to that body. So what does that mean? That even after escaping from the Earth, it goes to higher and higher distances, right? So let's say it has gone to, let's say, interstellar distance, very far away from the Earth. Then also it will have some speed over there. Why? Because initially we had given a lot of energy, but right now we are only giving minimum energy, and that minimum energy is your half mv square, the minimum energy, such that what would be the energy when it finally escapes? It's zero. Why? Why zero? Because when it has escaped, the potential energy would become zero, isn't it? Because it is at very, very far away from the Earth. Similarly, it has already escaped, and I'm saying it is the minimum initial energy. The final kinetic energy would become zero, because after escaping, let's say its velocity is zero. Okay, so what we are doing, basically we are just doing conservation of energy, right? So here What will be total energy over here? Right, let me write it over here. So total energy would be, just have to add them up, right, over R, and here plus half m VE square, right, and this would be equal to 0, right, after escaping it has become 0. All right, so just take this term to that side, small m and small m will get cancelled, right. So what does it become? See, it becomes Gmm by R, this you have taken to that side, equal to half m VE square, isn't it? And if you see over here, m and m will get cancelled, 2 comes over here, so VE square, we get an expression for VE square, right. Let me write over here, VE square is equal to 2Gm by capital R. Okay, 2Gm by capital R. So what would escape velocity? One expression we have got, isn't it? So let me write over here one expression. VE is equal to under root 2Gm by capital R. And again I am repeating, this is escape velocity from the surface of the earth. Okay, and in terms of acceleration due to gravity, also you can write an expression. How? Remember we had studied about acceleration due to gravity. What was the formula for that one? If you remember, right, acceleration due to gravity, G was how much? Gm by R square, right, Gm by R square, right, and from here what would be capital Gm? That is small g into R square. Take this R square term to that side and you substitute it over here, small g into R square, small g into R square, then R square and R will get cancelled, so you will get another expression, right, that would be under root 2 G R, right. Again this is at the surface of the earth. Okay, I hope this one is also clear. We can find another expression as well, another expression in terms of density. Okay, density of who? Density of our planet, which is earth. How exactly? See, just now I said a few moments ago that in place of mass you can get the expression for density. How? In capital M, right, in place of capital M you can do, let me write over here, right, capital M is what? Density into volume. Density is, let's say, rho. Volume is how much? It is a sphere. So what will be volume of the sphere? 4 by 3 pi r cube, right. Take this and substitute over here, right. So what would that become? What will this become? Under root 2 G, notice carefully, this will become interesting, you will get an interesting expression. So capital M you substitute over here, so it becomes rho 4 by 3 pi r cube, right, whole divided by r, isn't it? Whole divided by r, and if you see over here, r and r cube, they will get cancelled, and what would be left? R square would be left, right, and rest they will nothing would get cancelled, right. So we get another expression over here. Can you tell me the expression? See carefully, 2 into 4 by 3, it is 8 by 3. So under root 8 by 3, then you have pi rho and g, right. So pi rho g, and then you have last but not the least r square, right, r square, right, r square. So if you see 3 different expressions, one we have got from the other, right, this one we got from this only, and this third expression also we got from the first one. So please remember this first expression, okay. So don't get confused, this first expression is the most important among all 3. So let's see the question, what it is asking in the question, right. If you read the question carefully, they are saying escape speed from the earth's surface is VE. They have already said it is VE. The escape speed from the surface of a planet whose radius is half and mean density is double. So we have changed the planet, the radius is also changed, right, the radius has changed and the mean density has changed. Mean density we had written it as rho, radius is r, right? Radius is your r. So which formula we will use for escape velocity? Radius and density variation, right? This one we have to use. We can't use this one, right? Because here the mass term is coming. So if you want to remove the mass, you do it like this, you will get this formula only. So directly we will do, see, escape velocity is proportional to which terms? This one and this one, right? Because see, pi and g, they are constants. So I'm directly writing, see here, directly writing escape velocity is proportional to, right, under root rho and r square, right, rho and r square. Now let us start with our the planet that we are asked to find out, right? So let's say escape velocity on that planet surface is v dash, and escape velocity on our planet Earth surface is ve. This they have already given, right? Equal to under root. On Earth, what is the mean density? Let's write it as rho. On Earth, the radius is how much? Radius of Earth is, let's say, r only. So rho r square. This was for Earth. Now what about the planet? For the planet, they have said the mean density is double of that of Earth, right? So this becomes 2 rho. And on the planet, whose radius is half, so r becomes, instead of r, we will write r by 2. Or, see over here, r by 2 whole square, right? R by 2 whole square. Now you have to cancel the terms, that's all. See, rho and rho cancel out, r square and r square cancel out, and what would remain? See, under root 2 into 1 by 4 will remain, right? That is 1 by root 2. Okay, so from here you are getting the expression, see, v dash, it is nothing but ve by root 2, ve by root 2, right? So that means the correct answer would be option number 3, right? So in this question, if you remember the expression, we directly did, right? Nothing complicated. All right, so let's move on. Yeah, so let's do some interesting questions on this topic as well. If you remember, last time we had a question for this topic, right? And I believe you already know the formula as well for this one, right? So let's say, for example, two bodies we are having. Let's say this one's mass is how much? Capital M1, and this one's mass is capital M2, and their centers are separated by some separation. Let's call it as small r only. Now what will be the potential energy of this system? What would that be equal to? This potential energy, you can write it down. Let me write down over here. Minus G, right? I had repeated the same formula last time as well, right? Now what is this potential energy? What is this potential energy and why is it negative, right? Because remember, it is written potential energy of a system. So that means we did some work to make this system, to make this configuration, right? Now how will we do that work exactly? So let's say, for example, mass M1 is lying over here. It is lying over here, but mass M2 is not there, right? Mass M2, I am taking it from infinity to over here, okay? This mass M2 is initially not there, but from infinity to here, I am bringing this mass, okay? From infinity to here, I am bringing this mass. So let me write down over here, right? So work done by external force, right, in bringing which mass? That this one, mass M2, right? In bringing mass M2 from infinity to our point, right? To, let's say, to that point. Let me just write down, to that point. Equal to. Now if you see carefully, that work done would be in what direction? First you need to understand, and whether that work done would be positive or negative. Okay, how will that be? So please see, this M2 is at infinity, right? Now this gravitational force, that also we had discussed, that the force is an attractive force, right? Which means these bodies are pulling each other, right? So let's say M1 is pulling that body towards itself, isn't it? That means if you just leave this body, it will automatically, it has to go over this body, right? Which obviously does not happen. But if I am bringing this mass M2 from infinity to this point, right? So the gravitational force will be in which direction? Towards left, right? Gravitational force on this M2 will be this way. And remember the displacement, this mass M2 is coming from infinity to over here, right? The displacement of M2 is also in this direction, and the force is also in this direction. So we do integration, right? Over a small dr, we write the work, find the work done, and then we integrate. But whether that work done will be positive or negative. So for work done by gravitational field in bringing this mass from infinity to this point, that work done has to be positive. Okay, why? Because the gravitational force is also towards left, and the mass M2 is also, we have moved it towards left from infinity to over here. So work done by gravitational force will be positive. What about this one then? The external force is acting always opposite to the gravitational force, right? So work done by external force, it has to be negative. Okay, so the answer will be negative. And what was the expression? This is what we call as potential energy of the system. And what was the potential energy formula I wrote over there? Minus G M1 M2 by R. So over these past few seconds, I just explained why it's coming as negative or why not positive. Okay, so similarly, if I write down work done by gravitational field, right? Gravitational field, that would has to be how much? That will be positive, right? I just now told you work done by field is positive over here in this case. So it will be nothing but plus G M1 M2 by R. Okay, or you can remember this by another method as well, right? Work done by gravitational, work done by external force, right? Work done by external force, that would be nothing but change in potential energy. You can remember it that way as well. If you do it by that way also, you will get the same expression, right? So I'm writing another formula for this one, okay? So let me write over here, what is this expression? Final minus initial. Final potential energy minus initial potential energy. Okay, now what about this one? Work done by gravitational field will be how much? Initial minus final, okay? So for that one also you will get the same expression, that is initial minus final, that will be equal to, okay, plus G M1 M2 by R. Okay, if you want I can explain again why this comes at positive, right? Because remember, what is U initial for our example? Initially it was at infinity, right? So that means at infinity U initial will be how much? 0. So this U initial would be 0. Then what about U final? Finally means it has come over here, and here potential energy is how much? This much, right? So 0 minus G M1 M2 by R. That minus minus will get cancelled. So the answer is coming as plus. Okay, so I have interlinked a few things over here. So let's do our next question, right? So let's see if you are able to do this one. See, it's a very simple question. They are asking us, saying that 3 equal masses are kept fixed in the form of an equilateral triangle. That means the side length is A. And they are asking what is the potential energy of the system. Yeah, good afternoon Danish. What is the potential energy of the system? Now just not I told you, right? For 2 masses the potential energy is minus G M1 M2 by R. That's all. So here 3 masses. So what you have to do, you have to form pairs of masses, right? So how much pairs you are getting? This is one pair, this mass and this mass. Then this is another pair, and this will be the third pair. So only 3 pairs you will get over here, right? And for each pair you will get a potential energy term, isn't it? So let's say for this pair, how much is the potential energy? Again, don't get confused. This has to do with which concept? This concept. So here if you see, here we are not bringing that mass from somewhere to somewhere, right? We have just assembled this configuration, and here they are asking potential energy. You can directly use that formula. So for this pair, it is how much? Minus G M1 M2, M into M. So M square by R. R is how much? A only, right? A only. Okay, for this pair. Now what about this pair? The same thing. Minus G M square by A. Then for this pair the same again, minus G M square by A. You have to add them up. Add them up meaning multiply by 3 times, right? And now you have got the answer, right? So which one is your answer? Okay, it was very simple, right? If you know what we are doing, okay, that's it. All right, now let's take another question. See over here, in this one, see what I'm saying. Again, the question is beginning in the same way, right? Everything has been settled in the form of an equilateral triangle of side A. But now we are doing something else. What are we doing? What is the work done on the system, right? On the system. On the system means by who? By some external agent, by an external force. If the side of triangle is changed from A to 2A. So initially it was A. Finally, that side has been made 2A. So what you have to do? First, this is regarding which topic? The topic we did later on, right? Which is work done by external force and the field. So initially, right? Initially, what is the potential energy of the system? We did just now, right? When the side length is small a, the potential energy was minus 3 g m square by a, isn't it? See this question? This is what I'm talking about. Initially, this was the system, right? Then what is happening? An external agent is used to increase this side length to how much? 2a. 2a. Now just think carefully and tell me that work done should be positive or negative, even without solving any of this. You can tell me whether that work done should be positive or negative, right? Why? Because see here, all these masses, they are attracting, right? Attracting each other, pulling them towards each other, isn't it? So if you see here, this mass m is being attracted by both of them. That means that this system, it wants to become smaller and smaller, which won't happen, but it wants to become smaller. Now what you are doing? You are trying to increase the side length, which means this triangle becomes a bigger triangle, right? So let's say this mass, I am pulling it towards the outside, and this mass has to go outside because the triangle is also becoming bigger. So what I'm saying, the force is, let's say, towards right. The displacement of this mass is also towards right. That means that the work done on this mass is also going to be positive. So this, whatever be the answer has to be positive, right? If you see over here, answer has to be positive, right? So from this itself, if you see 3 options, they have vanished, right? Which means this is going to be the answer. But let's see. Let's see whether they will come as positive or not. Let's check. So this is U initial, right? And what will be U final? Very quickly, right? Simply we have changed the side length. So what will it become? Minus 3g m square by 2a. This topic is a little tricky, and some students find it a little difficult, so that's why I'm discussing. Okay, and what was the work done formula? By external agent or external force, what was it? We wrote the formula, right? U final minus U initial, U final minus U initial. So final was how much? Minus 3g m square by 2a. U initial has a minus sign, here also minus, so you have to take the LCM. Take the LCM, this becomes 2 and this becomes 6. So 6 minus 3 is plus 3, right? So it will be, answer will be plus 3 g m square by 2a, right? So I hope you guys have understood about this sign business, right? So even without solving this question, you could have directly ticked this answer, because this is the only one that has a positive sign. But still we have solved it and the answer is matching, all right? So work done by the external agent is this much. And see the next question. The same question, but here, what will be the work done by the system? By the system meaning, which forces I'm talking about? The gravitational forces, right? Because they are the ones acting in the system. So work done by the system meaning work done by the gravitational force, right? So work done by the gravitational force, or let's say I'm writing it as field for now. Which field? You already know, gravitational field I'm talking about, right? So work done by this field, what was the formula we had written? U initial minus U final, isn't it? You can see if you want to check. U initial minus U final. Work done by gravitational field is U initial minus U final. And that is the exact reverse of this one, right? And if you see over here, so let me write down U initial minus U final. And U final minus U initial, just now we found, what was it? Plus 3 gm square by 2a. So what will this become? Minus 3. Okay? And The correct answer would be option number 4. Okay. Obviously, this work done is going to be negative. So I hope you have understood, right? Why it is negative? Why this work done is negative? Because let's choose any one mass. Let's say this mass we are choosing. The net force on this mass is, let's say, in this way. Okay, I'm not trying to find the direction of that field. Just in a general sense, I'm saying it will be towards, let's say, towards left. And this mass is going to, this system is going to expand. So this mass is moving towards right, but the gravitational force is towards left. Both are in opposite direction. The work done will be negative. And as you can see, the work done is also negative. Okay, and you can remember it like this. All right, very well. Very well. Moving on to our next topic, laws of motion. Right? We have done lots of questions from this one as well. We had drawn FBD diagrams, right? Force body diagrams for each mass, and we had done some questions. So let's see what this question entails. See here, what are they saying? 3 blocks are given, okay? A, B, and C of masses 4, 2, and 1. 3 blocks are given, and they are said they are in contact. Contact meaning which forces would be acting on these masses? The normal force, right? Normal force would be acting on each body because of that touch, and they are standing on a frictionless surface. This is a frictionless surface, so there is no friction on this surface. And they said force of 14 Newton is applied on this 4 kg block, right? This is 4 kg, isn't it? This is 4 kg, and then this one is 2 kg, and this is 1 kg. And they are asking the contact force between the blocks A and B. So only between A and B we have to find the contact force. So there is a lengthy way and there is a shortcut method as well. Okay, what is that lengthy method? The one which you have already done, right? Which is you draw these blocks separately, draw the forces acting on them separately, then write Newton's second law for each of them separately. That is F net equal to ma, F equal to ma. You have to write for each block and you will get your answer. Okay, but here let me tell you guys a shortcut method for this one. Okay, that method is lengthy, isn't it? Because for each block you have to write separately. Asking contact force between blocks A and B only, not for B and C, right? So first, before beginning itself, let's find the acceleration of this system, right? So what will be the acceleration? This is going to move towards right, isn't it? Acceleration is nothing but the total net force acting on the body in the direction of motion, which is how much? F only, right? Because that normal forces are internal forces for this system. So for acceleration, I am considering the whole as a system. For the whole system, net force is F only, okay? F net over M total, okay? You can remember it like this. So F net is nothing but your F only, right? F upon, what is the total mass? 4 plus 2 plus 1, right? How much? 6 plus 1, 7, right? 7. So F is how much? 14, I believe, yeah. This comes out to be 2 meter per second square, 2 meter per second square. And remember the contact force between A and B they are asking. So contact force will act on which surface? On this surface, isn't it? They are touching each other over here. So if you draw the FBD for, let's say, A and for B and C, I am taking B and C as a whole full system, right? So let's say this is our A over here and this is our system, right? So let me draw the system like this. Okay, I hope which system I am referring to, right? This is your B plus C. Okay, so for this system, what are the forces that are being applied? See, on A you have F, and for what about this one? They are going to, see here, B plus C will apply a normal force towards this direction, A on that direction, right? So I can draw it like this. A will apply a normal force in that way, and B plus C we can say will apply normal force in this way. Okay, but again remember, let me again repeating that this normal force is actually acting on block B only on block B. But for now we are taking this whole as a system to simplify the question. Okay, so you can write Newton's second law in both ways. You can write Newton's second law for this one, you will get your answer N, or you can write directly for this one. I am writing for this one. We are doing the shortcut method, isn't it? So for this one, write this Newton's second law. What will it become? See, F net equal to M into A. F net is how much for B plus C over here? F net is how much? N only, right? M total is how much for B plus C? B plus C. 2 plus 1 is how much? 3. Into A. A is how much? 2. Right? So answer you have got 6 Newton. Okay, so I hope you have understood what we did over here. Okay, here also we have done M into A only. Alright, M into A. But this is which M? I hope you have understood, right? This is which M? This for B plus C we have written the M. Okay? If you want, you can take this as a homework as well, right? Draw the FBD for each block and write the Newton's second law and just check whether the same normal force you are getting, right? Same normal force as in 6 Newton whether you are getting. Very well. Now, this also you can take it as a homework, right? Here if you see, I am asking you for the same question, I am asking you find the contact force between blocks B and C. Only B and C, which means which surface you have to focus on? This surface, right? This surface, which means that normal force will act on C in the right direction and C will apply a normal force on B in the left direction, right? Left direction, and you can use that shortcut method. Again, okay, you can check, right? Yeah, C was 1 kg, right? So you can check whether you are getting this as the answer. So please check, do the same method, you can check this, you can take it as a homework. All right, very well. Okay. So I hope you guys are finding this session interesting. Okay, yeah, so some have replied. Danish Roadster, yes. The answer to that question was 6 Newton, and for the second one it will be 2 Newton, you can check. All right, so let's come to mechanical properties of solids. And if you see, under this topic, multiple times we have talked about that bulk modulus formula, right? Bulk modulus, and even if you see this question also pertains to that same topic, right? Bulk modulus of liquid. What are we doing? We are increasing the pressure, and what will happen? This also we have discussed, right? Let's say this is the fluid mass or fluid volume, and we are applying pressure on all sides, isn't it? So I'm applying pressure like this. I'm increasing the pressure. What will happen? That fluid will compress, right? So the volume will decrease, isn't it? And that's what they are saying. Read the question. The increase in pressure required to decrease the volume of liquid by this much. So this is how much? This is the original volume. Okay. This is the original volume, 200 liter. And what is this one? Fractional change in volume. Or we can say fractional decrease in volume, because we have increased the pressure. Okay, so this is nothing but your fractional decrease, or delta V by V. You can remember it like that. So what was the formula for bulk modulus? Let's do it quickly. Bulk modulus was minus delta V by V, right? Okay, so if delta P is positive, if you are increasing the pressure, volume will decrease. Okay, that is why this negative sign is coming into play, because bulk modulus has to be positive, it cannot be negative. All right, yeah, thank you, Danish. All right, let's see here, bulk modulus is given, fractional change is also given, we have to find the change in pressure, that is delta P we have to find, right? So delta P becomes how much? Bring these terms to that side, and we are only focusing on their magnitude. You can just forget about this negative sign, or let me write the negative sign as well, it doesn't make a difference, right? So B into minus delta V by V, right? B is how much? They have given 2100 kilopascal, kilo meaning delta V by V is fractional change in volume, and this delta V by V is going to be negative because volume is decreasing. That minus is taken care of by this minus. Okay, so I'm directly writing the fractional change, that is how much? This percentage, right? That is 0.004%. Percent meaning divided by 100. Okay, if you solve it, you will get the answer. And if you note, this initial volume, that had no role to play over here, right? It had no role to play because this delta V by V was already given. So we can solve it, right? If you see here, 100, see here, they will get cancelled, right? This becomes 4 by 1000. 4 by 1000, and this is also 1000, 1000, 1000 cancel. So what remains? 21 into 4, isn't it? So the answer will be 84. Yeah, 84. Yeah. So someone has said B and C may 2 Newton contact force. Yes. For the second question, yes, 2 Newton is the correct answer. All right, very well. So I hope you have understood this question. Okay. Yeah, and see this one as well. This is also a very similar question, or literally the same question almost. See, here the decrease in pressure I am asking. On that one I had asked increase in pressure. Here I am asking decrease in pressure, and the same initial volume is given, but here this 0.004% is what? It is the increase. Okay. It is the increase in volume. Increase in volume. Okay. So please remember delta V by V, that will be how much? 0.004 by 100. But this delta V by V will be positive. Okay. And that delta P will be negative over here because that pressure is decreasing. And here also if you solve, if you want you can solve it. But here also you will get the exact same answer, 84. Okay. You guys can solve it. You can take it as a homework. It was literally the same question. Okay. So moving on to our last topic of the day, work energy and power. Right. Under work energy we had discussed a few formulae for kinetic energy. Then we had talked about potential energy. So what will be the formula for potential energy? Let's see. See this question. What I was saying. A girl of mass 40 kg sits in a swing of this much length. So she is sitting. Right. So she is sitting meaning. So let's say this is a swing. All right. Okay. This is a swing. And here she is sitting over here. Okay. So let's say here the girl is sitting. All right. So let me draw it like that. The girl is calmly, comfortably sitting. And the total length is also given. L is given as 6 meter. And the person pulls the swing to the side. Pulling meaning I am pulling the swing to the side, which means this is going to rise up. Right? So rise up meaning what does it now become? See, it now becomes like this. The girl is also obviously sitting again over here. And so that the swing makes an angle of 60 degree with the vertical. So this angle theta is given with the vertical 60 degree, right? And they are saying find the gain in potential energy of the girl. All right, so here also she is sitting. Okay. So now can you tell me what will be the gain in potential energy? So for that I'm again giving you a trick, which is let's say take the lower level as potential energy equal to 0. Okay, so I will just write it down. 0 potential energy over here. Right, 0. How much height she has risen? She has risen by this much height. See, this is not height. This will be the height, right? So if you see this distance, it is your small h, right? So she has risen by small h. So what will be the gain in potential energy? It will be nothing but how much? mgh. Okay, m you know, g you know, h we can find out. How we are going to find out? See, this is L and this is theta, and if you see this is a right angle triangle, right? And if you see what is this length, this is also L only, isn't it? So that means what will become this length, right? This length I am talking about, right? Let me erase this one. Now it will be clear. I am asking about this length. This one will become how much? Hypotenuse cos theta. So L cos theta. This will be L cos theta, and theta is how much? 60 degree, right? So L cos 60 degree, cos 60 is 1 by 2. So it becomes L by 2, right? Yeah, Study Empire is asking 200 volume for what? That was the initial volume that was given. Okay, so irrespective of that, the delta V by V is also given. So we directly used it in our formula for bulk modulus to calculate the whatever term is being required. All right. So that initial volume did not come into play. That's what I was trying to stress over there. Okay, see here, this total length is given, becomes L by 2. This full length is L. So what will become small h then? Small h would be how much? Small h would be nothing but total minus this much length. That is L minus L by 2. So if you solve it, it becomes L by 2 only. Right? And now you can find out mgh. What would that be equal to? mgh. M is how much? 40 kg. 40. G is not given, right? G is not given. You can take 10 or you can take 9.8 as well. It will depend on the question, and in some questions G will be written, or if not written, let's say we are taking it as 9.8 over here, 9.8 meter per second square. H you found out, L by 2. L was how much? 6 meter, so 6 by 2, right? So you have to solve this one. See, 6 2 get cancelled, 3. It becomes 120. 120, so this becomes 12 into 98, right? 12 into 98, and if you solve it, this would be your answer, 12 into 98. Or let's say, for example, if this is 100, you have taken 10, this would have become 100. So 12 into 100, 12 into 100 would be 1200. So the answer would be close to 1200, that is this one only. Okay? Very well. Very well. So we have come to the last question of the day, right? Now see this question, what are they saying? A spring is stretched by 1 centimeter, right? For this one, you have to take that the spring is initially in equilibrium, right? It is in equilibrium position. From that equilibrium, you are stretching it by 1 centimeter. So what would that become? And they are talking about stored energy, right? And what will be the energy of the spring? It is half k x square, whether x is compression or elongation. Here x is how much initially? 1 centimeter. 1 centimeter, or in SI unit you will write it as 0.01 meter. So this is our spring energy, or let's call it initially, and then finally what does it become? They're saying it is further stretched by 1 centimeter. So after 1 centimeter, again by 1 centimeter we are stretching. Total stretch would be 2 centimeter, right? So here you will write half k x square or half k. Okay? And they have also said initially it was storing 50 joule, right? So initially it is 50 joule. So instead of over here, let me directly write 50 over here, okay? And then what are we going to do? We are going to take the simple ratio. So UF by 50, right? So just take the ratio simply, final by initial equal to half k will get cancelled, 0.02 square by 0.01 square, right? Okay, and what does this become? See, 0.02 and 0.01, they will get cancelled, and what remains? 2 only. So it becomes 2 square, right? 2 square is nothing but your 4. You take this 50 to that side, take this 50 to this side, 50 into 4. 50 into 4 will be how much? 200 joule. Okay? Alright, so we have come to the end of our session, and I hope you guys had a great time, and